So to finish off pipelining, what we're going to be looking at are some of the problems dealing with it, how branching affects it, and what we're looking at in terms of performance. And this is going to be broken down into a theoretical portion we can use to do some metrics on code bases to figure out what we can expect on a system. And we'll also be looking at the different architecture evolution of CPUs. So if we remember back to the previous lecture, really what we were looking for is the idea of I can have multiple units, so to speak, and each unit does something like fetch, decode, execute, so to speak. And the goal is to be able to keep each one of these units running every single time the CPU ticks. Now, let's consider this particular problem. I have an add S here. Okay, this add happens. Then I have a branch that happens. Okay, which instruction should be put into the pipeline after this branch? Because if I put this instruction in there, then this instruction in there, and we actually go through in this, in other words, I've got these two in the pipeline, and since they're in the pipeline, they're going to be going through there while this one isn't finished. So if it is equal to 0, then we're going to be in real trouble, because we have to blow away the pipeline for the right instruction to be put into this. So let's do this example, that way you can see what I'm talking about. So once again, label each instruction. A, B, C, D, E, F. So let's assume that, let's say register 2 holds 3, register 3 holds -3. Or sorry, R2, R3. So what's going to happen is we have our different units. I have fetch, decode, operands, execute, and store. So time 1, A is going to be fetched. Time 2, A is going to be decoded. B is going to be fetched. Time 3, A, B, C. Time 4, A, B, C, D. Now, at this point in time, when A goes to store at time 5, we have a little problem here. B can't execute until A is finished. Because remember, I need the conditional code for this thing to be finished. So unless our CPU says, oh yeah, I've set the conditional code after it gets out of the execute phase, then you can't execute B the next time around. So B just kind of sits there, and C and D just kind of sit there, because this is a no op. And then at time 6, A is finished. Then B goes to execute. C, we get the operands for it. D, and then E. Well, the problem is when we come over here to B, and we finally get down here, because those are equal to 0, I have to essentially blow this entire pipeline out. Because in terms of circuitry, it's going to be almost impossible to say, oh yeah, this is the one, like check to see if this instruction's in the pipeline and leave it alone. That circuitry is extremely complex, so it in general is not used. So B is going to, when it's storing, it's going to clear out the pipeline. So at time 7, well, now I'm going to go to done. So guess what? E is going to get chunked into the pipeline. Time 8, E, and then F. And then E and F, so on and so forth. So this is an example of where branching can be a real problem in terms of performance. So these are the two major issues that happen. We see the idea of a bubble, which is where the instruction depends on the value of the previous instruction. So my pipeline is stalled until the instruction is finished. That's a bubble. And then we saw how when we have a branch, we can have a pipeline clear that completely blows everything out of the water. So as we saw, branches flush things. And after a branch, our pipeline is just going to sit there and go, don't have anything to do. We call that a no-op. To a smaller extent, load and store are the same way. Now, you may be thinking, why would that be the case? Because it's not a branch instruction. Well, they don't necessarily clear the pipeline, but what they do is they slow things down. Because remember, CPU is here physically. There is basically silicone and then a wire that's going to come over here to RAM, and we are basically stuck with this thing called electricity and physics. And just by those rules, it is going to be slower to access memory because it's different than what's on the CPU itself. So sometimes it may just add an extra cycle whenever we load or store something. That's dependent on your architecture. So when we have an extra cycle, that's called a delayed load and store. Now, obviously branches, this is not a new problem. This is something that has been known from day one, so to speak, with programming languages. So how do we get around this? The answer is what is called a speculative branch. If we think about a simple approach to this, load the next instruction after the branch. However, the branch fails, then you blow away the pipeline and go about your business. But if we've got something that says, okay, before it took this path, well, let's go take that path this time and see if it works, so to speak. So there are all kinds of different policies in terms of how we determine which branch we should take. So if we think about different instructions and the orders of them, and when we think about pipelining, it's a really good thing. However, if we're not careful, we can blow away this entire idea of pipelining. Now, what do we mean by that? So if I've got, let's just say these 2 lines of code. I'm going to add 10 to the value of register 1. My next instruction is going to take that value and store it into register 2, or the address stored in register 2. So what's the problem with this? Well, the problem is until I have stored this value, I cannot fetch the operand for the next instruction. So essentially, if we remember our different stages in the pipeline, I have fetch, decode, fetch operand, execute, and store. Well, instruction 1 is going to be over here, instruction 2 is going to be here, and I've got a 2 pipeline bubble because these instructions fit next to each other. Now, what is this like in a higher level programming language? So C is A plus B. Okay. This one is just fine by itself, but the problem is C is needed down here for this one. So if I do C equals A plus B up here, I don't want this next one. F equals G plus H doesn't have anything to do with this either. So these are completely independent, and they can run right next to each other and no problem whatsoever. And I come down here again, and I have an M equals K plus L. Okay. So we have essentially, if we look at this, I have 3 instructions that are unique to each other, that they have no pipeline, I guess you could say, implications. Now, I also have 3 that are dependent, so to speak. So now I'm going to say D equals E minus C because this gives me the most distance between the instructions that are dependent. So essentially, I should be able to fully fill the pipeline and not have to worry about bubbles if I reorder it this way. And the second one is J equals I minus F. And the last one is P equals M minus N. So when we look at this ordering of the code is better performant because of pipelining. Now, before you knew about pipelining, would you have even cared about what order you put operations in your code? Probably not. But if we're really looking to get performant, so to speak, you write code this way. Now, most people don't worry about this level of performance. However, if you have calculations that are happening in something that needs to happen 60 frames per second, sometimes every little bit counts. Seriously. The other part of this to consider is the idea of a compiler. Because a compiler should be able to determine how big of a pipeline it's targeting, because it obviously needs to know the CPU, so it should know what the pipeline depth is, and then should be able to detect instructions that are dependent on previous ones. So if you remember back to that whole optimization thing that we talked about in the very beginning when it came to compilers, that's really what we're looking at. It's just one thing that can happen with a compiler. So that kind of gives you, that's basically the answers, but that gives you the idea of this. So if we look at our code, let's just think about standard, let's gather information, so to speak, about this. Our goal for this is really to come up with the idea of a metric. In other words, if I can look at my code base line by line, analyze how it's going to execute, I should be able to start being able to tell some information about the pipeline on it. So we have this term called CPI average. Ideally, if we think about cycles per instruction, I want every instruction to happen one cycle after the other after the other. Because one is the best where we're going to get. We can't execute an instruction faster than one clock cycle. Now, we're never going to get that in real life because of branches. Because how many of you have written a program that doesn't use an if, a while, or a function call? And essentially hello world doesn't really count. So any major real program is not going to have our ideal pipeline. So if we think about a way to analyze source code and a way to say, okay, how performant is our code to take advantage of the pipeline? So we have some basic terms we need to define, or variables, in our mathematical equations. We have B, which is a branch penalty. This is known because we can, based on the CPU, we know the number of cycles that are going to be lost because of a branch because of our pipeline size. So the pipeline size is usually 4 on a RISC architecture because, well, guess what? You blow away the pipeline. And then you refill it, so to speak. Now, this probability of an instruction being a branch. If you do static analysis of your source code, you can determine the number of lines of code in your program. You can determine which features of your program are branches. In other words, if statements, while loops, for loops. So we can determine what's the probability of, if I execute any program, any line of code in this program, what's the probability that that is a branch instruction? And then we have CPI, no branch is 1. So average is 1 minus the probability that a branch has been taken, multiplied by essentially what the no branch amount is, plus the probability of hitting a branch. So if the probability of a branch is taken is 0.25 and a branch penalty is 4, so I have 1 minus my probability, which is 0.75, times 1. So I don't need to do that. Plus, in this case, the probability of hitting that. So 25 times that, so that's 1. So I believe our CPI average is 1.75. So when we look at this, 1.75, it's not quite twice as bad, but it's essentially saying because of branches, our code base is almost slowed down 100%. In actuality, 75% because of branches. Now, we also have the idea of speculative pipelining. So we have a branch penalty, probability of instruction being a branch, and now we have the idea of the probability of a branch that is being taken is correct, so to speak. So we have the same basic idea for this, but now I have the probability of the no branch and the regular branch. So that gives us if we were to go through all just the basic plug and chug, we could figure out what the CPI average for that is. So our goal for this is just understanding we can come up with metrics to say, okay, how performant is our code in terms of a pipeline? Now, are you ever going to actually have to do this math? Well, not in this class. I'm not expecting you to analyze code and tell me how performant it is or do those metrics. Think about cases where this matters dramatically. We have 4 billion instructions per second on a 4 gigahertz CPU. unless we have branch after branch after branch after branch, things are going to execute pretty fast for most things. However, if you run into performance problems, this can be one easy way to fix problems, because in many ways this goes back to the previous section. I'm talking about inline programs and all of that, and thinking about, well, if I just simply reorder some things, maybe that'll fix it. So any processor's execution efficiency is basically no branch divided by the average. So that's really just to give you an idea of, we can use some math to model a code base to say, okay, here's what we think is actually going to happen in terms of speed. So if this happens, then you compare it to the average number of assembly instructions it takes to execute every line of code and the pipeline fill for that. And it gives you an idea of your real performance that you can expect out of a code base. And once again, unless you're trying to do something in real time, or you're trying to hit 60 frames per second or higher, you may not ever have to worry about that. Now, the next thing we're going to do in terms of looking at performance is, well, we've seen how pipelines work. How do they fit into a CPU itself, and what does the CPU look like? Now, we're not going to jump into Ryzen versus i9 to begin with, because those CPUs are the result of decades of work. And it's kind of hard to start and say, oh yeah, let's look at something that's been built on top of 40 years worth of effort, so to speak. Because back in the 80s, we had this little thing that looked just like this. Now, if we think about these pins, we're talking about these little metal feet. If we think about this, there are 40 of them, which means there are 20 on each side. What does that mean? Each one of those is essentially a 1 or a 0. So there are 20 on each side, or 40 total. So that means we can have at most 40 bits either coming in or out of this at the same time. But then we've got things like power and ground, or some of those bits. So when we look at it, if you've only got to worry about, say, 40 odd connections, if you had to manually wire one of these, it would take a little while to manually wire 40 connections, but it would be doable. It may take you an hour or two, but you could wire up one of these CPUs. Inside of this, it had 7 registers. It had 78 instructions. It did not have megabytes or gigabytes of memory. It addressed 65,536 bytes. Remember, a byte is 8 bits. So if we think about 78 instructions, so 2 to the 4th is 16, 2 to the 5th is 32, 2 to the 6th is 64, 2 to the 7th is 128. So when we look at this, 7 bits are necessary to reserve, to specify, hey, this is the particular instruction I'm looking for. So if this is a 7-bit instruction, so to speak, so if we think about it, at minimum, this is an 8-bit CPU. If I have this number of bytes of addressable memory, I can figure out just how big my address space is, so to speak, because I know how many bytes are there, if if I have this particular number, I'm going to have 2 to the something, which will tell me the number of bits address-wise, so to speak, are necessary for this. Even back in the beginning days, it had programmable stacks, because otherwise you can't have functions. If you can't have functions, you can't even really write software. And this started out at 2 megahertz. So if we think about a hertz, that's sort of like 1 per second. A kilohertz equals 1,000. A gigahertz is a billion. So you can see where megahertz lies in terms of the performance spread for this. Now, how did this thing work under the hood? In other words, what's inside of it? So this address bus and this control bus are what we're looking at to say, okay, how do things get into this and out of it? So when we think about it, we have 16 bits. That's what we're looking at. Now, when we look at all of these parts, okay, I have an instruction register. Guess what? The program counter is going to point to something, and it's going to get pulled in, and it's going to store the instruction somewhere. Guess what? Then it's going to be decoded. And obviously the person who wrote this doesn't know how to write decoder. And once we have that particular piece, okay, we've got the other parts that this thing is going to happen. Now, if we have a mux, that's basically just a selector which says, okay, this one or that one type thing. Now, basically what happens is we have these parts, but in addition to going to the register and the decoder, it's going to go through and figure out, well, which register are we talking about here? Now, remember, we described the number of registers that were available on this. They're all here. And then I have a selector to say which one of those registers I'm pulling out of. And we have our program counter, we have our stack pointer, some other parts. Basically, we pull off part of the instruction and add it to a base address, and that's where we get this piece here. And we have our ALU in this. So when we think about a 40-odd-year-old CPU, yeah, it's kind of complex. It's got lots of different parts to it, but it's not so far out of the realm of possibility that we can't understand it. Because each of these parts are not extremely complex. I mean, we know that, okay, over here we don't quite understand how adding and all of that works, but it's not all that difficult to say, okay, well, I've got some circuitry here. I have some registers that hold the stack and the program counter. I have my registers and the inverse of them. We won't get into why you store the inverse. And then we've got our whole pipeline part here. So architecture is not all that amazing. So when we look at this A through H or 0 through 7, now how in the world did they do some of these instructions? Well, one of the interesting things about the original CPU is, unlike in Raspberry Pi where we can specify, hey, here's where the results are stored, everything was always stored in A. Why did they do that? Well, if I always know where something's stored, guess what? That frees up space in the instruction so I don't have to specify where it goes. Sometimes an instruction required certain registers to be used. In other words, if I'm doing like a double add or something, I'd have to store the results in B and C, store the values in B and C to call the instruction, and it would hard code where those two are. and it has a 1-byte register that stores the state of the machine, which is the conditional code. 64K memory, 2 to the 16th. It's an 8-bit CPU, no direct way to handle 16 bits, but it could use 2 registers to handle 16 bits. It had a stack pointer that was maintained by the programmer, and there were some instructions that made this a little bit easier. Program counter, we've already talked about that. Instructions could be 1, 2, or 3 bytes of memory. So they could be 8, 16, or 24 bits. And interesting, if you look at the manual, it cautions against storing data and instructions together. Remember that whole data and text section? Well, that came all the way back from the 80s. Addressing, it could be done directly using a register, could be done with immediate, which is an instruction that basically gives us an address into memory. It had a stack for essentially the first and second places in the stack to get memory. How did you write code for that CPU? Well, it had a label, a code, and an operand, and it had comments. Data could be stored in hexadecimal, binary, or octal. Could do basic operations. Could move things from one address to another, and it had the idea of jumping. And everything worked at a 2's complement, and if you have that in 122 or 322, you understand that, and we'll cover that more later on. But if we think about this, 40 years ago, that's how assembly looked. How much different is that than what we have today? Not a lot. We have labels. You have the opcode, so to speak, like move, add, so on and so forth. And then in our case, we have potentially, like, say, 3 operands instead of just 1. We have dot word in our current assembly. Well, define word, define byte, so on and so forth. Had basic instructions, comparison, fun instruction called DAD, which is the double add. And I'm not going to go through all of the instructions, obviously, but I'm just showing you that 40 years ago, this is what assembly was. It had a move instruction. It had an add instruction. The syntax is a little different, but in general, it's the same thing. So if we think about it 40 years ago versus today, in terms of assembly, we haven't advanced much. Not that there's been any real need to advance. Stacking is just as simple as pushing a pair of registers on, popping the pair off, so to speak, and incrementing a pointer. Now, I did all that just simply to talk about what something a long time ago could do. Now, you may think, why in the world would we be talking about a 2 megahertz CPU and what it could do? Well, that's what ran the original Nintendo 8-bit system. Now, it wasn't an Intel CPU, and it wasn't exactly 2 megahertz, but it had more registers, but in the same basic vein. So if you really know what you're doing with assembly code, you can accomplish something that's pretty incredible. Because if we think about this, 1985, we're almost 40 years away from the beginning of this. And how many people know Super Mario? And all this was accomplished using an extremely simplistic CPU that you can understand. Now, CPUs did not stay simple. If we went from the 8080 to the Pentium 1, well, now we've got the idea of an instruction cache. I have 8 kilobytes of instructions and 8 kilobytes of data stored on the CPU. We've still got instruction decoding. Well, guess what? We're doing some fetching here. I have a branch target buffer. In other words, that speculative execution we're talking about. We'll get into this later with terms of memory. Now I can see my data is 64 bits, address is 32 bits versus 16. Guess what? We've got floating point registers. We've got our basic arithmetic, so to speak. I have two different parts to my ALU. I've got a shifter, registers. I mean, we've added on a few bits, but it's about the same thing. So they made it larger and they added some cache to it. When they went the next step to the Pentium Pro, well, guess what? They have an instruction cache, they have decoding, they went to the register mapping table, operands. So our fetch operand went to this part. Once all of those parts were there, then I had the instruction, which could then be executed. And then once it's executed, then it's stored. So when we got to the Pentium Pro, it essentially said, okay, we're going to follow roughly what the pipeline we just talked about is. Now, obviously, there are some more parts to it, but we can see how long it took for each one of these cycles, so to speak, to happen. So I know if we think about 3, 6, 9, 11, 12, and then 14. So we have 13 or 14 CPU cycles. So these CPUs ran at 60 megahertz sometimes, depending on what the Pentium Pro is, or somewhere around in that range. It's been a while, so I could be wrong on that. So you took the performance and divided by, say, 14 to be conservative, and that told you how fast this thing could execute instructions. Guess what? We move up to the Pentium 3. Now we're starting to get a little more complicated, because instead of just one cache, guess what? We've got two caches, level 1, level 2. We've still got our instruction cache. Now I have better branch prediction. We're at 512 entries for this. This can decode 3 instructions at the same time. And then it's building this up to say which are these going to use, so to speak. And we can have 20 different entries that are going to be in this that could potentially store addresses, load them, do different things, so to speak. And then once we've got that, I can reorder. In other words, these may be happening in parallel, but I want the output to happen in a particular order. And I've got my data cache. So they keep refining, they keep adding things in, they keep making them better. And then, well, we'll skip the whole Pentium 4 thing, but essentially what we've done with modern CPUs is saying, okay, everything we just talked about is going to be stuffed into this little core thing right here. So we duplicate this, and in this case we have 4 of them, and then our cache is down here. So if we think about it, if we look at it in terms of the size for this, right here is about half of the CPU thereabouts. So if we think about it, it's almost 20, it's not quite 20, it's not quite 50%. It's somewhere around 25-30% of the CPU is just dedicated to memory. And then we have these parts here that are designed to get things into the CPU from RAM as fast as possible. And then we have the slower input here, and then we have maybe 10% dedicated to controlling memory. And AMD hasn't just kind of set back and copied Intel's work. AMD CPUs right now are considered superior than Intel's. So they have a 64 kilobyte instruction cache that is decoding 4 instructions instead of 3 per cycle. We have 6 of those little instructions pulled out at the same time. We have integers and floating point. We figure out which one we're going to do, so to speak, or schedule each part to go into each one of these units. And I can do 2 loads and a store per cycle with this. And I have a cache with this. So there are all sorts of different ways for these CPUs to work. I'm not going to expect you to understand or talk about or say, oh yeah, let me draw out the Intel 1 architecture. I just want you to be aware of what's underneath the hood of these and why we talk about pipelines, why they're important, and how they affect real CPUs themselves. Because CPU development is pretty amazing. However, it's a double-edged sword. It's extremely complex to build a modern CPU. There's no way a new company can easily create a CPU that is going to compete with what we currently have. Which means we're kind of stuck with what we've got for the most part. Some people are looking towards the next generation or quantum computing. Some people are looking at different materials, completely different off-the-wall things. But in general, you got ARM, you've got Intel, you got AMD. That's it. Now there are specialty CPUs for niches. I'm going to look at GPUs, but that's really what we're looking at for this. And hopefully you've seen when and why you would even consider going low level. You should not be thinking about the order of your higher level code instructions as you're writing them. Typically, you're going to want to really think about, well, what can I do instead of worrying about optimization? Get the thing working. Get your architecture built. Think about that first. Then identify bottlenecks in it. And once you have the bottlenecks identified, then you can start saying, well, what's causing this? Is it pipeline related? Is it memory related? What are we doing with this? So you can start to think about what the parts that are being extremely slow are doing, and then that might let you come up with a better fix to solve it. So, in a nutshell, that is pipelining.